The ground in western Nevada has been shaking every single day since April 5th, over 400 earthquakes in 18 days. And they are moving east toward Utah, toward 2.5 million people sitting on top of a fault that has been locked and silent for 1,400 years. We will track this swarm mile by mile from the first jolt to the city directly in its path. We will look at the invisible forces cracking the crust open, the historical chains that show how bad this can get, and the question scientists still cannot answer. If this video reaches you in time, like and subscribe. We are just getting started. Brace yourselves, we begin. April 5th, 2026. A normal Tuesday morning in Churchill County, Nevada. Then the ground moved. Not a single jolt. And done. The earth beneath western Nevada started shaking and kept going. Dishes rattled off shelves. Car alarms screamed in empty parking lots. People in Fallon stepped outside, looked at each other, and waited for it to stop. It did not stop. For 18 straight days, the ground shook continuously. Hundreds of small jolts, one after another, some barely felt, some strong enough to crack walls. Scientists watching their monitors stared at data that looked wrong. Earthquake swarms happen all the time in Nevada. They start, they fade, they end. This one refused to end. The trigger was a magnitude 5.7 earthquake, the size of a hit that can collapse poorly built structures and send shockwaves across an entire region. It ruptured the crust near Silver Springs and Fallon, two small towns sitting in the flat Nevada desert, about 60 miles east of Reno. The rupture was deep and sharp. It sent energy radiating outward in every direction, like a stone dropped in still water. What followed was the body's response. When rock fractures underground, the surrounding crust tries to settle into a new position. Smaller faults nearby slip a little. Stress redistributes. You get aftershocks. Every major earthquake produces them. Scientists call the pattern Omori's Law, a rule established over a century ago that describes exactly how aftershock frequency decays over time. Fast at first, then slower, then gone. The April 5th swarm ignored that rule completely. The shaking did not decay on schedule. Instead of fading inside a week, the activity held steady, then shifted. Geologists watching the data noticed something strange around April 13th. The earthquakes were not clustering in place anymore. They were drifting. That detail matters more than anything else about this story. A swarm that stays in one spot is manageable. Stress releases locally. Faults adjust. Life moves on. A swarm that moves is something else entirely. Moving seismic activity means energy is traveling through the crust, finding new faults, waking up rock that has been sitting still for decades. Western Nevada sits on some of the most fractured crust in North America. The region has been stretched, cracked, and pulled apart for millions of years by forces deep below the surface. That stretching created hundreds of parallel faults, running roughly north to south, like cracks in a dried-out piece of clay. When one of those faults slips, the stress does not disappear. It transfers sideways, loading onto the next fault in the chain. Picture a line of dominoes set very far apart. A normal aftershock sequence tips the first one and stops there. The gap is too wide, but the April 5th swarm did not stop. The energy kept jumping the gaps, activating faults that had no recent history of movement, pushing deeper and farther into the interior of the American West. By the end of those 18 days, scientists had logged over 400 events across a corridor that stretched hundreds of miles, 400 separate moments where rock deep underground snapped, shifted, or slipped, and every single one of them was pointed in the same direction. The question was not what started this. The question was where it was going, and when the data made that destination clear, the conversations inside geology offices got very quiet, very fast. What scientists saw on those maps changed everything about how they were looking at this swarm. Most people have heard of the San Andreas Fault, one clean line running through California, the fault everyone pictures when they think about earthquakes in the American West. Movies have been made about it. Cities have been built around it. Scientists have studied it for over a century. The Walker Lane does not get the same attention, and that might be the most dangerous thing about it. The Walker Lane stretches across western Nevada and eastern California, running roughly parallel to the Sierra Nevada mountains. From above, it looks like a massive scar across the landscape, hundreds of miles wide and over 1,000 miles long. But unlike the San Andreas, which is one defined fracture you can trace on a map, the Walker Lane is a web, a dense, branching, tangled network of faults that cross and overlap and interact in ways scientists are still working to fully understand. That structure is what makes it different and more unpredictable. The Walker Lane handles a stunning amount of tectonic work. The Pacific Plate and the North American Plate are grinding past each other constantly, a slow collision that has been happening for tens of millions of years. The San Andreas Fault carries most of that motion, but the Walker Lane absorbs somewhere between 20 and 25% of the total movement between those two plates. That is a massive share of force being distributed across hundreds of broken, interlocking faults, instead of one clean line. When you spread that much stress across a fractured network, things get complicated fast. A single fault, like the San Andreas, builds pressure steadily and releases it in large, somewhat predictable ruptures. The Walker Lane releases stress through constant low-level activity, occasional swarms, and rolling sequences of moderate earthquakes. Geologists call it a diffuse plate boundary, meaning the energy of two colliding continents is bleeding out across a wide zone rather than snapping at one seam. That sounds safer. In practice, it creates a region where stress can travel in unexpected directions and activate faults that appear quiet on the surface. The crust inside the Walker Lane is highly fragmented. Geologists sometimes compare it to a mosaic made of broken tile. Each tile is a block of crust sitting at a slightly different angle, moving at a slightly different speed. When one block shifts, the pressure on every block around it changes instantly. That ripple effect is what allows earthquake energy to travel across the region in ways that standard models struggle to predict. Here is the part that keeps researchers paying close attention. The Walker Lane is getting more active over geological time. Data suggests the fault system is gradually capturing a larger share of the plate motion that the San Andreas currently carries. The Walker Lane is, very slowly, becoming the dominant boundary between these two massive plates. That process takes millions of years, but on a human timescale, it means the region is under increasing stress right now, in the decades and centuries we are living through. The April 2026 swarm did not appear out of nowhere. It appeared in a zone that was already loaded, already fractured, already primed for exactly this kind of cascading activity. The swarm lit up the Walker Lane the way a match lights a room you already knew was full of gas. And the room does not end at the Nevada border. What lies at the eastern edge of all that traveling stress is the part of this story that changes the stakes entirely. April 5th started quietly. No warning signs the instruments could have caught in advance. No unusual animal behavior reported. No strange ground deformation detected in the days before. Just a normal spring morning in the Nevada desert. Dust on the roads, sky wide and pale blue. Then, at a depth of several miles underground, a wall of rock gave way. The magnitude 5.7 main shock hit the area near Silver Springs and Fallon with enough force to send shaking across a region the size of a small state. People in Reno felt it 60 miles away. Residents in Carson City stepped back from their desks. In Fallon itself, the shaking was sharp and physical, the kind that makes your body react before your brain catches up. A magnitude 5.7 is a serious earthquake. On the scale scientists use, each full number represents about 30 times more energy than the one before it. A 5.7 sits comfortably in the range where damage occurs. Water mains crack, older buildings lose chunks of their facades, and anyone standing near shelving units regrets it immediately. The rupture tore through faults near Fallon that had slipped before. This region of Nevada has a documented seismic history going back well over a century of recorded observations. The faults here are known. Scientists had mapped them. The area was watched. So when the magnitude 5.7 hit, geologists activated standard monitoring protocols and expected what always followed, a normal aftershock sequence. The first few hours matched predictions exactly. Dozens of smaller earthquakes rattled the area in tight succession, each one a little weaker than the last, the crust releasing tension along the newly ruptured edges. By evening, the shaking had slowed enough that locals started assessing damage and checking on neighbors. Then the next day brought more earthquakes, and the day after that. By April 12th, over 1 week into the sequence, monitoring stations had logged dozens of magnitude 2 to 4 events, still hammering the same region. That alone was unusual. Most sequences of this size quiet down substantially within 72 hours. A week of sustained activity at that level meant something in the stress field was staying elevated. Geologists looking at the data noticed the aftershocks were not shrinking toward a single point as expected. Instead, they were spreading, not randomly the way a splash of water fans out in all directions, in a pattern, a directed linear pattern that had a clear orientation. Scientists use precise instruments called seismographs to pinpoint exactly where underground each earthquake originates. When you plot those origin points on a map over time, you can see whether a swarm is clustering, scattering, or moving. The April 5th swarm was moving. That directional drift told researchers the main shock had done more than break one fault. It had disturbed the stress field across a wide area, loading energy onto faults that sat outside the immediate rupture zone. Those faults were responding. One by one, slowly, they were slipping. The 5.7 should have been the story. One earthquake, one cleanup, one entry in the records. Instead, it opened something. The next chapter of this swarm would arrive on May 1st and make the original main shock look like a warm-up act. Science runs on patterns. An earthquake happens. Aftershocks follow. Then they fade. That sequence is so reliable that geologists built a mathematical law around it over a century ago. The law is named after a Japanese scientist who first described it in 1894. It says aftershock frequency drops in a very specific predictable curve over time. Fast decay at first, then slower, then quiet. Every major earthquake sequence since then has followed this curve closely enough that scientists use it to forecast how long shaking will continue and how strong the remaining aftershocks might be. Emergency managers rely on it. Insurance companies use it. Governments build disaster response timelines around it. The April 2026 Nevada swarm broke that curve. The first few days matched perfectly. Seismometers across western Nevada recorded the standard rapid decay. Scientists watching the data relaxed slightly. The sequence was performing as expected. Forecasts went out. The shaking would taper off within the week. Then around April 13th, the numbers stopped cooperating. Instead of continuing to fade, the rate of earthquakes held steady. Then it shifted location. The seismic energy was not dying out at the original rupture site. It was appearing in new places, slightly farther east, slightly farther south, like a slow leak spreading through a cracked pipe. Seismologists have a name for this behavior. They call it migration. A swarm migrates when the earthquakes are being driven by something other than simple mechanical relaxation after a rupture. Normal aftershocks happen because the rock directly around a fresh rupture is unstable and needs to settle. They cluster in one spot. They fade. Done. A migrating swarm means something is actively pushing the stress forward. Two main forces can do this. Pressurized fluids moving through the crust, carrying energy with them as they travel. or a slow, silent sliding of rock deep underground that transfers load onto new sections of fault without making noise of its own. Both of these mechanisms turn a local event into a traveling one. The April swarm showed characteristics of both. Scientists watching the spatial data saw the leading edge of earthquake activity advancing roughly 1 to 2 miles per day through the crust. That rate is consistent with fluid-driven migration where underground water or geothermal gas percolates through fractures and lubricates faults along the way. But the depth profile complicated the picture. Some of the migrating earthquakes were originating at depths consistent with aseismic slip, the silent kind of movement that leaves no seismograph signature until it hits a friction point and generates a quake. That deeper signature suggested the crust itself was moving slowly and dragging the stress eastward through the rock. What made this unprecedented in the recent record for this region was the combination, fluid migration and aseismic slip working together across a single connected fault network, both driving the swarm in the same direction at the same time. Scientists identified this pattern in peer-reviewed studies after the fact. During those 18 days, they were watching it happen live and struggling to model what came next. The swarm was not decaying, it was traveling, and the path it was carving through the Nevada crust pointed toward a fault system that had been sitting quietly for a very, very long time. What that fault had been storing up during those 14 centuries of silence is the detail that changes this from a Nevada story into something much larger. Pull up a geological map of the western United States. Give yourself a moment to look at Nevada. The state is covered in parallel mountain ranges running north to south, separated by flat valleys. From above, it looks like a giant hand dragged fingers through wet clay and left ridges behind. Every one of those ridges sits on a fault. The valleys between them formed because the crust dropped while the ridges stayed up. Now imagine plotting every earthquake from the April 2026 swarm as a dot on that map. Day 1, the dots cluster tightly near Fallon, Nevada. A small, bright constellation of seismic activity grouped around the original rupture. Normal. Expected. Nothing alarming yet. Day 5, the cluster is still there, but a few dots have appeared slightly to the south and east. Barely noticeable. Could be random scatter. Scientists note it and move on. Day 10, the pattern becomes impossible to ignore. The dots are forming a line. A clear, almost geometric line extending out of the original cluster and stretching across the map in a single consistent direction, toward the east, toward Utah. By day 18, that line of earthquake dots crosses 310 miles of crust, cutting through the Basin and Range province like a drawn mark on paper. The line does not wander. It does not branch wildly. It follows the orientation of a connected fault structure running through the interior of the American West, moving steadily toward the Wasatch Mountains and the valley beneath them, where Salt Lake City sits. Scientists looking at this map called it a mechanically continuous fault structure, a technical phrase that describes a chain of faults connected deeply enough underground that stress travels between them. On the surface, these faults look separate, isolated, quiet, but down at depth below where you can dig or drill with standard equipment, they share the same crustal plumbing. A lone magnitude 4.7 earthquake appeared on a fault hundreds of miles from the main swarm, triggered in isolation with no local main shock to explain it. That single outlier event lit up researchers. An isolated earthquake on a historically quiet fault, appearing at exactly the right time and exactly the right place along the migration path, suggested the stress wave had already reached that far. One dot, hundreds of miles ahead of the pack, a signal flare sent from deep underground. The path from Fallon to Salt Lake City is roughly 500 miles by road, through the desert, across mountain passes, past towns so small they do not appear on most maps. The fault structure connecting the two does not follow the road. It cuts beneath the surface in a nearly straight line, through rock that has been under building pressure for over 14 centuries. For anyone living along that line, the map was not an abstract scientific chart. It was a trajectory, and at the end of that trajectory sat a metropolitan area of 2.5 million people who had never experienced a major earthquake in their lifetimes. The straight line on that map told one half of the story. The other half lived underground, in the mechanics of a fault that had been gathering energy since before the first Europeans set foot on this continent. That fault has a name, and its history is the scariest part of this entire swarm. Earthquake sequences are supposed to get quieter over time. The first hit is the biggest. Everything after it is smaller. That is the rule. Seismologists call the largest subsequent event a largest aftershock, and it reliably falls below the main shock in magnitude, sometimes by a full number, sometimes more. The sequence winds down. Life returns to normal. On May 1st, 2026, the Nevada swarm broke that rule with a magnitude 5.2 earthquake striking near Silver Springs at a depth of 7.45 miles underground. 7.45 miles is a specific number, and it matters. Shallow earthquakes, those occurring in the top few miles of crust, tend to produce sharper, more damaging shaking at the surface. A quake at that depth hits the ground with focused energy. Residents across Churchill and Leon counties felt it immediately as a sharp, violent jolt, different in character from the rolling motion of deeper events. The magnitude 5.2 came 26 days after the original main shock. 26 days. In a normal sequence, a second significant event arriving nearly a month after the initial rupture would be extraordinary on its own, but combined with everything else happening in this swarm, it carried a specific and alarming message. The energy level was holding. The sequence had not exhausted itself. The stress field beneath western Nevada was still actively rupturing new sections of crust, finding new fault surfaces to slip on, generating new main shock level events rather than fading into background noise. Scientists classify earthquake sequences into 3 categories: main shock aftershock sequences, where one big event dominates and the rest are smaller; swarms, where many events of similar size occur over an extended period with no clear single largest event; and foreshock sequences, where a cluster of activity precedes an even larger rupture. The May 1st earthquake raised the possibility that this sequence was shifting into the 3rd category. A foreshock sequence looks almost identical to a swarm from the inside. The only way to know which one you are experiencing is to wait and see what happens next. If a larger earthquake follows, the earlier events get reclassified as foreshocks. If the sequence dies out, they remain classified as a swarm. There is no real-time test that tells you which path you are on. That ambiguity is exactly what makes this kind of situation so difficult to communicate to the public. Scientists cannot issue a warning based on a probability they cannot precisely calculate. They watch, they measure, they model, and they share what the data shows while being honest that the data has limits. What the data showed after May 1st was a sequence that had produced 2 main shock level events more than 3 weeks apart, with hundreds of smaller earthquakes in between, all migrating steadily in the same direction across a fault corridor connecting Nevada to Utah. The 26-day gap between the 2 largest events was the detail that made researchers most uncomfortable. Most sequences consolidate their energy quickly. The fact that this one recharged and fired again nearly a month later suggested the stress source was deep, sustained, and still active. The ground in Churchill County shook again that day, and somewhere far beneath the desert floor, east of where anyone was looking, the crust absorbed a little more pressure. The path ahead was about to get a great deal more complicated. 2 large earthquakes in one sequence is unusual. 3 is rare enough to trigger serious scientific attention. 4 events of comparable magnitude inside a single swarm, occurring within weeks of each other in the same region, falls outside the boundaries of what standard seismological models are designed to handle. The April 2026 Nevada sequence produced 4 distinct main shock level events clustered within a single magnitude unit of each other, meaning the largest and the smallest of the 4 were very close in energy, separated by a small fraction of the earthquake scale, rather than the dramatic drop-off scientists expect between a main shock and its aftershocks. Standard models are built on a simple assumption: one rupture does the most damage, then everything else is cleanup. The biggest event breaks the most rock, releases the most energy, and sets the ceiling for everything that follows. Aftershocks are by definition smaller. The models treat the sequence as a pyramid, wide at the bottom with many small events, and narrow at the top with one dominant main shock. A sequence with 4 events crowded near the top of that pyramid is something different. Scientists call this a multiplet swarm, a cluster where no single event clearly dominates and the energy distributes across several nearly equal ruptures. Multiplet swarms happen, but they are far less common than standard main shock aftershock sequences, and they carry a distinct warning built into their structure. When 4 earthquakes of similar size strike in rapid succession, it suggests the fault system is not breaking cleanly. A clean break releases the accumulated stress in one sharp event. A system that produces multiple similar-sized breaks is a system that cannot find a single clean rupture surface. The stress is trapped in a network of smaller faults that keep slipping without fully relieving the pressure. Think of trying to break a thick piece of wood with your hands. If the grain runs straight, it snaps in one clean crack. If the grain is tangled and irregular, the wood splinters in multiple places, and you end up with a ragged fracture that never fully separates. The Walker lane is tangled grain, deeply tangled, built over millions of years of stretching and fracturing. Each of the 4 main shock level events in this sequence broke a different section of that tangled network. Each one transferred stress to adjacent faults. Each one contributed to the migration pattern pushing the swarm eastward. Together, they created something more alarming than a single large earthquake would have. They created a sustained, multi-source stress transfer across the entire corridor. For geologists running computer models of the stress field, 4 similar-sized events are harder to simulate than one large event. Each rupture changes the geometry of the stress field, which means every model you run after the first earthquake is already working with outdated starting conditions. Scientists had to continuously update their stress maps as each new event occurred, and each update revealed the fault corridor was absorbing more load than the previous model had projected. The picture building from this data was not of a swarm winding down. It was a map of progressive loading, each event passing the baton eastward to the next fault in line. The last fault in that line had been waiting for 1400 years, and the baton was still moving toward it. Picture the American West from the air, flying east from Reno at high altitude. Below you, the landscape stretches out in a rhythm: mountain range, valley, mountain range, valley, over and over, the same pattern repeating across Nevada and into Utah, as regular as a heartbeat. This is the Basin and Range Province, one of the most geologically active stretches of land on the continent. The pattern you see from the air is not decoration. Every mountain range down there sits on a fault. Every flat valley formed because the crust between those mountains dropped. The whole region is actively being stretched apart, pulled in opposite directions by forces originating deep in the Earth's interior. The crust is thinning. The faults are alive. Running through this stretched-out landscape is a 310-mile corridor of connected fault structures, confirmed by peer-reviewed structural geology research. This corridor links western Nevada to the eastern edge of the Basin and Range, where the crust finally meets the thicker, older rock of the Colorado Plateau and the Rocky Mountains. Along this corridor, the April 2026 swarm left a trail. Scientists tracking the migration of seismic events mapped each earthquake as it appeared along the path, watching the sequence advance day by day through the desert. The earthquakes were not random scatter. They followed the corridor's orientation with a precision that ruled out coincidence. What made researchers particularly alert was the activation of historically quiet faults along that path. Faults that had produced little or no recorded seismicity in the modern monitoring era suddenly generated events during the swarm. The most striking example was the isolated magnitude 4.7 that appeared on one of those forgotten faults far ahead of the main cluster. That event had no local trigger. The only explanation consistent with the data was that stress had traveled along the corridor and reached that fault before the swarm's visible leading edge did. 310 miles of cracking, adjusting, stress transferring crust. To give that distance a reference point, it is roughly the same as driving from New York City to Boston and adding another hour on the highway. That is how far the seismic energy traveled through solid rock in less than a month. The corridor does not end at the state line. The fault structures documented in geology research extend eastward into Utah, where they connect to the frontal fault system running along the western edge of the Wasatch Mountains. The Wasatch Front, as it is known, is where the Basin and Range province meets a very different kind of rock. The transition zone between stretching crust and stable continent creates one of the most mechanically stressed regions in the interior of the American West. A 310-mile trail of earthquakes pointing like an arrow connects the April 5th main shock site directly to that transition zone, and at the far end of that arrow, sitting in the valley below the Wasatch Mountains, is a city that most of its 2.5 million residents have never felt a major earthquake shake. The fault beneath that city carries enough stored energy to change that in a matter of minutes. What that fault has been accumulating underground since the year 626 is the next piece of this story. Most people picture earthquakes as purely mechanical, two slabs of rock, locked together, building pressure until they finally snap. Pure force. Pure friction. No other ingredients. The reality is wetter and stranger. Deep beneath the Nevada desert, the earth is not dry. Water, steam, and pressurized geothermal fluids move constantly through the cracks and pores of the crust, pushed upward by the intense heat below and by the pressure of everything sitting on top of them. Nevada sits on one of the most geothermally active regions in North America. The heat from the Earth's interior bakes water deep underground into high-pressure fluid that has nowhere easy to go. When that pressurized water finds a crack, it enters. When it enters a crack in a fault, something remarkable happens. The fluid pushes the two sides of the fault apart, ever so slightly, reducing the friction between the rock faces. Geologists call this effect pore pressure reduction. But a simpler way to picture it is this. Take two rough pieces of sandpaper and press them together hard. They grip. They resist. Now spray water between them. The grip disappears. Pressurized fluid does the same thing to a fault. A fault that needed enormous force to break suddenly requires far less. The fluid does not create the stress. The tectonic forces do that. But the fluid lowers the threshold between a locked fault and a slipping one. It tips the balance. Scientists studying the April 2026 Nevada swarm found strong evidence that fluid migration played a central role in the eastward drift of earthquake activity. The rate at which the leading edge of the swarm advanced through the crust matched what geologists observe in documented fluid-driven seismic sequences around the world. 1 to 2 miles per day, a pace too slow to be simple mechanical stress transfer, but too fast to be purely a seismic slip. Nevada's geology gives fluid a direct path to travel. The crust in the Basin and Range province is riddled with fractures running in parallel orientations, all pointing roughly in the same direction, because the regional stretching created them that way. Fluid entering those fractures follows the grain of the rock, moving preferentially in the direction the faults run. In this region, that direction is east. The fluid is not a thin trickle. Geologists estimate the volumes moving through active fault systems during a major swarm can be enormous. Forced through the rock at high pressure by the combination of geothermal heat below and tectonic squeezing on the sides, the fluid front moves ahead of the visible earthquake activity, lubricating faults before they slip, setting up the next rupture before the current one has finished shaking. This means the swarm's leading edge was arriving at faults along the corridor before any seismograph could detect it. Silent preparation happening ahead of the visible action. The fluid theory explains a great deal about the April swarm's behavior, but it does not explain everything. Some of the migration signatures in the data pointed to something even quieter than fluid movement, something that leaves almost no trace at all until a fault finally gives. That second mechanism is the reason scientists were watching the deep crust beneath the entire corridor with extreme care. There is a kind of earthquake that produces no shaking, no rattling windows, no alarm systems, no damage reports, no moment where anyone stops and says, "Did you feel that?" The ground moves, rock slides against rock, stress transfers from one fault to another, and the entire event passes through the crust without registering on a single seismograph. The word aseismic means without seismic waves. No waves, no signal. No signal, no warning. A aseismic slip happens when two sections of fault slide past each other slowly enough that the rock deforms like stiff clay instead of snapping like a dry branch. Slow sliding does not generate the rapid vibration that produces earthquake waves. Instead, the fault creeps, millimeter by millimeter, transferring its load quietly and efficiently to every fault it connects to underground. From the surface, this looks like nothing. The landscape does not change. No cracks appear. No tremors ripple through buildings. But deep underground, the geometry of stress is shifting. Faults that were sitting comfortably below their breaking point are creeping closer to it. Locked sections of crust that had been stable for centuries absorb new load without any visible signal that something has changed. Scientists detect aseismic slip using extremely precise instruments called GPS stations and strain meters. These devices can measure ground movement smaller than a fraction of an inch over months of observation. During the April 2026 sequence, strain measurements across the Walker Lane corridor showed subtle surface deformation inconsistent with the recorded earthquakes alone. The visible seismic events could not account for all the movement the instruments detected. The remaining movement had to be coming from somewhere. Aseismic slip was the most consistent explanation. When a seismic slip reaches a section of fault that is fully locked, meaning a section where friction is high enough to prevent gradual creep, the silent movement stops. The stress it was carrying dumps onto that locked section all at once. The locked fault cannot creep to relieve the new load. It absorbs it, adds it to everything already stored there, and waits. The Wasatch Fault beneath Salt Lake City is a locked fault. 1,400 years of seismic silence confirm it is not creeping. It is holding. Everything that has accumulated there over those 14 centuries, every increment of tectonic stress from the Pacific Plate pushing against the North American Plate, every ripple of movement from the Walker Lane, stays locked inside that fault until the rock finally cannot hold anymore. Aseismic slip traveling along the corridor from Nevada toward Utah is, in a precise mechanical sense, a loading mechanism for the Wasatch Fault. Each quiet slip event along the path transfers a small additional package of stress eastward, adding to the total stored in that locked system. The terrifying part of this mechanism is the timing. Aseismic slip gives no warning before the final break. A locked fault, loaded by silent creep, does not announce when it has reached its limit. It simply ruptures, and the energy released in that rupture reflects everything accumulated over the entire silent loading period. 1,400 years of accumulation, a corridor actively transferring more stress toward it right now. And no instrument yet built that can tell you exactly when the threshold gets crossed. What history tells us about what happens when similar corridors finally break is a story Nevada itself has already lived through. 1954. Nevada was a different place then. Smaller cities, quieter highways, vast stretches of desert, with almost no one in them. The monitoring networks scientists rely on today barely existed. Seismographs were mechanical instruments, few and far between, recording on paper drums in university basements. The modern GPS networks and satellite monitoring systems were decades away. And yet, even with those limited tools, what happened in Nevada in late 1954 was impossible to miss. It started on July 6th with a magnitude 6.6 earthquake near Fallon. Large, damaging, the kind of event that collapses masonry and cracks foundations. Researchers documented it. Life went on. A large earthquake in the Nevada desert, significant but contained. Then, on August 23rd, another rupture, a magnitude 6.8, this time near Fallon and Stillwater. Stronger, more damaging. Scientists noted the unusual timing, 2 major earthquakes in the same region within weeks of each other, but the monitoring data was too sparse to draw confident conclusions about whether they were connected. Then December 16th arrived. In the span of a single 4-minute window, the Nevada crust produced one of the most striking sequences ever recorded in the American West. A magnitude 6.8 struck first. Seconds later, a magnitude 7.1 tore open the Fairview Peak Fault. Minutes after that, a magnitude 6.9 ruptured the Dixie Valley Fault system, leaving a visible scarp in the desert floor that stretched for miles. 3 major earthquakes inside 4 minutes. The faults had been loading each other for months. When one broke, the transferred stress was enough to break the next, which transferred enough to break the next. The scarps from the Dixie Valley rupture are still there today. You can stand in the Nevada desert and look at the physical evidence of what cascading fault rupture looks like. The ground on one side of the fault line stands several feet higher than the ground on the other side. The land itself recorded what happened there like a stone diary that has not been erased in 70 years. What the 1954 sequence demonstrated was something geologists had theorized but rarely seen so clearly in the observational record. Fault systems in the Basin and Range province are mechanically linked. A rupture on one fault does not simply release that fault's stress, it redistributes stress across the entire network, loading neighboring faults, sometimes past their breaking point, within hours or days. The Walker Lane was the highway those 1954 ruptures traveled, the same fractured, interconnected fault zone now carrying the April 2026 swarm. The distance from the 1954 rupture sites to the 2026 swarm epicenter is small enough that scientists can credibly argue they are part of the same regional stress system. The same crust, the same faults, the same underlying mechanics. 70 years passed between those events. Stress has been building quietly in the region ever since. And now a new swarm is traveling the same corridor, activating faults in the same sequence, following the same eastward migration. The dominoes are arranged differently than in 1954, but the physics has not changed. And the sequence building right now has something the 1954 chain never reached. A destination with 2.5 million people at the end of it. Reno, Nevada, February 2008. A small earthquake, nothing dramatic, rattled some windows near the edge of the city. Normal for Nevada. People went back to their coffee. Then another, and another. Over the following weeks, the area around Mogul, a quiet neighborhood on the western edge of Reno, experienced over 1,000 earthquakes. The largest hit magnitude 4.7, strong enough to knock items off shelves and send cracks through walls. The sequence ran for months, generating a level of sustained low-level shaking that Nevada residents called exhausting. Sleep disrupted night after night, small jolts arriving without schedule. No way to know if the next one would be bigger. Scientists descended on Reno to study the Mogul sequence up close, and what they found reshaped understanding of how earthquake swarms work in this region. The Mogul swarm had no obvious tectonic trigger. There was no large main shock that set it off. There was no major fault rupture in the area in the months before it started. By all standard measures, the region should have been quiet. The earthquake catalogue showed nothing alarming leading up to February. But deep underground, something had been moving for months before the first seismograph registered anything unusual. Geothermal fluid, pressurized by the heat of the Earth below the basin and range, had been migrating upward and sideways through a network of small fractures beneath the Mogul neighborhood. As that fluid moved, it entered the cracks surrounding a fault system that ran beneath the residential area. Pore pressure rose, friction dropped, and one by one, small fault sections that had been locked for years began to slip. The fluid did not create new faults, it activated old ones. Faults that were already there, already loaded with tectonic stress, just sitting below the threshold needed to slip on their own. The fluid pushed them over that threshold. Over 1,000 times, the Mogul sequence produced some of the clearest observational evidence ever recorded in the western United States for fluid-driven seismicity in an urban setting. Scientists tracked the spatial migration of the earthquakes underground and matched the migration rate precisely to the expected movement speed of pressurized geothermal fluid through fractured rock. Fluid moved, earthquakes followed. Fluid moved farther. Earthquakes followed farther. The relevance to the 2026 swarm is direct. Western Nevada sits on the same geothermal system that drove the Mogul sequence. The fracture networks are connected. The fluid sources are shared. The migration mechanics are identical, except the 2026 swarm is traveling 10 times farther than the Mogul sequence did, along a corridor 10 times longer toward a fault 10 times more consequential. The Mogul swarm stayed local. Over 1,000 earthquakes rattled one neighborhood for a few months, then faded as the fluid dissipated and pressure equalized. No one was seriously injured. The city absorbed it. The 2026 swarm is not staying local, and the fault at the end of its path does not have the same capacity to absorb stress quietly and move on. That distinction is everything, and it brings the story to the mechanism that most scientists agree makes this swarm uniquely dangerous: the way stress travels invisibly between faults across hundreds of miles of broken crust. Stand in the middle of Nevada and look at the mountains on either side of you. Those ridges did not form by being pushed up. They formed because the ground between them dropped. The Basin and Range province is a landscape being stretched, actively, right now, as you listen to this. The force pulling it apart comes from the movement of tectonic plates far to the west. The Pacific plate is slowly sliding northwest relative to the North American plate, dragging at the continent's western edge. Part of that drag transfers inland, creating tension in the crust that pulls it east and west simultaneously. The rock cannot stay whole under that tension. It breaks. When crust under tension breaks, it breaks along normal faults, where one block of rock slides down relative to its neighbor. The block that stays up becomes a mountain range. The block that drops becomes a valley. Do this hundreds of times across a region the size of the American West, and you get what Nevada looks like from an airplane: parallel ridges and valleys repeating from one horizon to the other. The Basin and Range province covers an enormous area, stretching from southern Oregon down through Nevada, Utah, and into Mexico, and from eastern California almost to the Rocky Mountains. The entire zone is extending. Scientists measuring the width of the province with GPS satellites have confirmed it is getting wider every year by roughly 1 to 1.5 inches annually across the whole system. 1 to 1.5 inches per year sounds tiny. Multiply that by 10 million years, and the crust has stretched more than 200 miles. The mountains you see in Nevada are the cracked and separated pieces of what was once a single coherent plateau. That ongoing extension means every fault in the Basin and Range is perpetually accumulating stress. The region never fully relaxes. It cannot. As long as the Pacific plate keeps moving and the tension keeps pulling, the crust keeps loading. Earthquakes release some of that stress, but never all of it. The faults fill back up. This is the long geological backdrop behind the April 2026 swarm. The swarm did not begin in a neutral region that happened to crack one day. It began in a region that has been under continuous active stress for millions of years, where faults are always within some fraction of their breaking point. The ongoing extension also explains why the swarm migrated eastward specifically. The basin and range is widest in the east and narrowest in the west, reflecting the direction the crust is pulling apart. Stress introduced at the western edge tends to travel toward the eastern boundary, where the stretching meets the more rigid crust of the Colorado Plateau and the Rocky Mountains. That eastern boundary is the Wasatch Front in Utah, the place where the stretching stops, where all the accumulated extension across 500 miles of cracking crust finally runs out of room to go. At that wall of rigid rock, the stress has nowhere to travel. It stacks up, it stores, and directly above that storage point, a city built in the 19th century has grown into one of the fastest expanding urban areas in the American West. The fault running beneath that city has been waiting at that boundary for 14 centuries, and the geological forces moving toward it right now have been in motion for far longer than that. On a quiet stretch of Nevada desert, far from the cluster of earthquakes near Fallon and Silver Springs, a seismograph recorded something that did not fit. A magnitude 4.7 earthquake, isolated, on a fault with almost no recent seismic history. No local main shock had struck nearby in months. No regional stress event should have reached that far based on standard decay models. By every measure the monitoring system used, that fault should have been silent. It ruptured anyway. A magnitude 4.7 is large enough to feel clearly. Anyone within 15 miles standing on solid ground would have felt the floor move beneath them. Objects on shelves shift, hanging lights sway, the kind of jolt that makes people step away from windows and check their phones for news. And this one arrived without any of the usual context. No cluster of foreshocks, no local main shock, no clear reason rooted in local fault activity. When scientists plotted the location of this isolated event on the migration map of the April swarm, it landed precisely along the eastward corridor, precisely in the zone where the traveling stress wave was expected to arrive based on the migration rate calculated from earlier events. The statistical probability of that placement being coincidental was extremely low. Seismologists reviewing the event concluded the most consistent explanation was remote stress triggering. The traveling stress front, driven by fluid migration and a seismic slip along the connected fault network, had reached that section of the corridor and loaded a local fault past its breaking point, triggering a rupture with no nearby main shock to explain it. Remote stress triggering is a real documented phenomenon. After very large earthquakes, the seismic waves traveling through the crust can trigger other earthquakes thousands of miles away in seconds. That mechanism is well understood, a slower version of the same process where stress migrates through fluids and aseismic slip over days or weeks and triggers distant ruptures, is less commonly documented but consistent with what geophysics predicts. The magnitude 4.7 in isolation would be a minor footnote in any normal year. A small earthquake on a forgotten fault in the Nevada desert. Scientists record it, file it, move on, but appearing at exactly the right place and exactly the right time along the migration corridor, it functioned as a tracer, a seismic marker that confirmed the stress wave had already traveled farther than the visible cluster suggested. The leading edge of the swarm was ahead of where the visible earthquakes indicated, running quietly through the crust, loading faults that had not yet announced themselves with any shaking. The magnitude 4.7 was the one that broke early and gave itself away. The others along that path were still holding, absorbing, waiting for the load to push them past their own thresholds. Scientists mapping the corridor after this event updated their models. The stress transfer had covered more ground than the previous day's estimates. The migration was faster than expected along certain segments, and the destination at the end of the corridor was receiving more load than the conservative projections had suggested. One small earthquake, alone on a forgotten fault, changed the scientific picture of this entire event. And what it revealed about the speed and reach of the traveling stress wave raised the urgency of everything scientists were watching downstream. Geologists have a phrase that sounds dry on first read, but carries enormous weight when you understand what it means: mechanically continuous fault structure. 4 words that, in the context of the April 2026 swarm, changed the conversation from "this is a Nevada problem" to "this is a regional problem." Here is what it means in plain terms. The crust of the Earth is not one solid slab. It is broken into countless pieces at every scale, from tiny fractures you can see in a rock sample to massive fault systems stretching hundreds of miles. Most of those pieces are separated. A fault in one valley is mechanically disconnected from a fault in the next valley by intact, strong rock in between. Stress can build on one fault and never reach the other because the solid rock between them acts as a barrier. A mechanically continuous structure is different. In this case, the faults are connected at depth, meaning if you could travel underground along the fault system, you would find a pathway of fractured, weakened rock running the entire length without a significant barrier breaking the connection. Stress introduced at one end can travel to the other end without dissipating into surrounding intact rock. Structural geology research published in peer-reviewed journals identified the corridor running from the Walker Lane region of Nevada eastward toward the Wasatch Fault in Utah as one of these connected structures. The research used seismic imaging, borehole data, and surface mapping to reconstruct the fault geometry underground. What that work revealed was a fault network connected deeply enough that a stress pulse traveling through it would not simply stop at the Nevada-Utah border. The borders humans draw on maps mean nothing to fault mechanics. For the April 2026 swarm, mechanical continuity transformed the migration pattern from a local curiosity into a long-range transfer mechanism. Every earthquake in Nevada that advanced the stress front eastward was doing so along a track that ran, without interruption, toward the Wasatch Front. Scientists studying this structure were not speculating that the stress might reach Utah. They were watching it move along a documented pathway toward a documented endpoint. The uncertainty was not about whether the corridor connected the two regions. The research confirmed it does. The uncertainty was about how much of the traveling stress would survive the journey and arrive at the Wasatch Fault with enough force to matter. Stress dissipates as it travels. Every rupture along the path bleeds off some energy. Every crack in the rock absorbs a fraction of the load. By the time a stress front travels 310 miles, it arrives weaker than it started. How much weaker depends on the specific geometry of the faults, the presence of fluid, the rate of aseismic slip, and dozens of other variables that scientists cannot measure with current technology at full resolution. The Wasatch Fault does not need much additional stress to become dangerous. It has already stored 14 centuries of accumulation. Any meaningful additional load from the Nevada corridor does not need to be large to tip the balance. A fault sitting just below its breaking point does not need a massive new push. It needs a small one. How close to that breaking point the Wasatch Fault currently sits is the question that determines whether this swarm stays in the history books as an unusual Nevada event or becomes the prelude to something that changes the American West permanently. There is a sound coming from the earth beneath the Walker Lane that most humans will never hear. Low-frequency vibration far below what human ears detect, registering on highly sensitive instruments buried underground across the Tectonic corridor in western Nevada and into Utah. Scientists call it seismic tremor, and during active swarm events, the instruments have been picking it up continuously. Seismic tremor is different from the sharp jolt of a standard earthquake. A typical earthquake releases its energy in a sudden burst, a snap that sends waves rippling outward in seconds. Tremor is the opposite. It is a sustained low-amplitude vibration that can last for minutes, hours, or even days. It has no clear start and no distinct end. It hums. The first major discovery of deep seismic tremor came from subduction zones, places where one tectonic plate dives beneath another. Scientists found that tremor in those regions often accompanied slow slip events, the aseismic movement, described earlier, where crust slides quietly without generating standard earthquakes. The connection between tremor and slow slip suggested the two phenomena were linked. That tremor was the acoustic signature of aseismic movement happening too slowly to produce conventional seismic waves, but generating faint vibration nonetheless. Finding tremor in the Basin and Range province, a stretching environment rather than a subduction zone, raised immediate scientific interest. The detection of sustained low-frequency signals across the Walker Lane corridor during the April 2026 swarm added another data point to a picture that researchers were assembling piece by piece. Tremor across a 310-mile corridor during an active swarm suggests the movement is not confined to the specific fault segments producing visible earthquakes. The entire corridor is vibrating, subtly, continuously, as deep fluid movement and slow aseismic slip work through the fractured crust simultaneously with the larger rupture events occurring at shallower depths. For anyone living along that corridor, the tremor is inaudible and unfelt. Surface vibration from seismic tremor is too small and too slow to register in the body or rattle a window. But for sensitive ground instruments, it is a clear and persistent signal that the crust is in motion across a wide area, not just at the specific points where earthquakes break the surface data. Scientists use tremor patterns to map where aseismic slip is occurring underground in real time. The location of tremor signals correlates with the location of slow slip on fault surfaces. During the April swarm, tremor detections tracked eastward along the corridor at roughly the same rate as the visible earthquake migration, suggesting the two processes were moving together. The visible earthquakes were the snapping points, the tremor was the background motion connecting them. A corridor of continuous humming from Nevada toward Utah, invisible to human senses, audible only to buried instruments, is the best real-time evidence available that this swarm was driving deep and widespread crustal movement far beyond the individual earthquake locations. That movement was approaching a fault that had been completely silent for 1,400 years. Seismically silent. No recorded tremor, no detected slow slip. No visible earthquakes, just locked rock, waiting, absorbing whatever arrives at its surface from the west. The contrast between the humming corridor and the silent fault at its eastern end is the most striking physical detail of this entire event, and the silence on the eastern end is the more alarming of the two. The idea that an earthquake in Nevada could affect a fault in Utah sounds like it should require some dramatic chain of events. A massive rupture, maybe. A visible crack running across state lines. Something you could point to and explain in a single sentence. The reality is more subtle, more invisible, and in many ways more alarming than a dramatic surface rupture would be. Stress transfer through the crust happens constantly, invisibly, and at distances that would surprise most people. Every time a fault slips, the rock around it rearranges. The geometry of the surrounding crust changes. Sections that were being squeezed get released. Sections that were relaxed get loaded. The changes ripple outward through the rock, weaker with distance but never perfectly zero. Scientists calculate this transfer using a model called Coulomb stress change, which maps exactly how a rupture event alters the failure potential of every other fault in the region. Coulomb stress change calculations from the April 2026 Nevada sequence showed measurable stress increases on fault sections along the entire eastward corridor. Measurable does not mean enormous. The numbers are often small fractions of the pressure required to break a fault on its own. But a fault sitting close to its breaking point does not need large additional stress. Any positive increment, no matter how small in absolute terms, moves that fault closer to failure. Picture a glass of water filled to within a millimeter of the rim. You can add a tiny amount and it overflows. The amount added does not need to be large. The glass was already almost full. The Wasatch Fault beneath Salt Lake City is that glass. 1,400 years of tectonic loading has filled it. The Nevada corridor is a slow, steady drip arriving at the edge. Coulomb stress modeling after major earthquakes has successfully retroactively explained many subsequent ruptures in connected fault systems. The 1992 Landers earthquake in California, for example, demonstrably increased stress on the fault that ruptured 6 hours later in the Big Bear earthquake, 20 miles away. The two events were linked by stress transfer, confirmed after the fact by the mathematics. Over longer distances and longer timescales, the same physics applies. The mechanism is slower and the stress increments are smaller, but the fundamental transfer of load from one fault to another through connected crust is the same process, operating at a larger scale. What makes the Nevada to Utah connection particularly concerning is the combination of factors all working in the same direction. Mechanical continuity of the fault structure, confirmed by geology research. Active fluid migration carrying stress eastward, evidenced by the swarm's migration rate. Aseismic slip adding silent loading to the corridor, detected by strain instruments. Tremor signals tracking the movement of all of the above in real time. And at the far end, a locked fault with 14 centuries of stored energy and a major city built on top of it. Each of these factors alone would be worth monitoring. Together, they create a situation that pushed Wasatch fault hazard assessment to the front of scientific attention in ways it had not been for years. The next chapter of this story moves east, to that fault, to that city, and to the ground it sits on. And what geology records in that ground about what happened there 1400 years ago should matter to every single person who lives in Salt Lake City today. When a fault slips, the earthquake ends in seconds. The shaking stops. The news crews arrive. Damage assessments begin. To everyone on the surface, the event is over. Underground, the consequences are just getting started. Every rupture permanently changes the shape of the stress field surrounding it. Rock that was being compressed from one direction might suddenly find that compression relieved. Rock that was under tension might find that tension increased. The changes are not temporary. They do not fade like ripples in water. The new stress geometry locks in place and becomes the baseline from which every future earthquake in the region will develop. Scientists call this static stress change. The word static is key. Unlike the dynamic waves that travel through the earth during shaking and fade within minutes, static stress change is permanent. The rock around a ruptured fault is physically different after the earthquake than it was before. Different in a way that either makes neighboring faults more likely to slip or less likely, depending on their orientation relative to the rupture. Orientation matters enormously. A fault running parallel to the one that just ruptured and positioned in exactly the right location might receive a large positive stress increase, pushing it significantly closer to failure. A fault at a different angle, even nearby, might receive a stress shadow, a region of decreased failure potential, where rupture becomes less likely for decades. Coulomb stress modeling maps these changes by calculating how the new geometry of the crust, post-rupture, alters the balance of forces on every surrounding fault plane. The calculations require knowing the exact geometry of the rupture, the orientation of surrounding faults, the mechanical properties of the rock, and the direction of regional tectonic loading. All of those inputs carry uncertainty, but the models consistently outperform random chance when predicting which faults become more active after a major earthquake. The April 2026 Nevada sequence produced not one, but 4 main shock level ruptures, each permanently altering the stress field before the next one occurred. Each new rupture was working in a stress environment already changed by the previous events. The cumulative effect of 4 significant static stress changes, all occurring along the same eastward corridor within weeks of each other, built a progressive stress increase that advanced farther east with each successive event. Scientists running Coulomb models after each main shock in the sequence updated their maps of which fault segments were receiving increased stress. After the first event, the stress increase was detectable along the corridor, but relatively modest at the eastern end. After the second event, the stress increment at the eastern end was larger. After the third and fourth events, segments of the Wasatch Front zone showed meaningful positive stress change in the models. Meaningful in this context means above the threshold that in historical cases worldwide has been associated with triggered earthquakes on receiving faults. The permanent reshaping of the stress field by these four events did something that the fluid migration and aseismic slip alone could not have guaranteed. It created a geometrically favorable pathway for stress to accumulate on specific segments of the Wasatch Fault. The segments geologists had already identified as most hazardous based on their loading history and position beneath the most densely populated parts of the Salt Lake Valley. The rock was rearranged, and the new arrangement pointed the loaded gun at a very specific target. Imagine a wall running underground along the western base of the Wasatch Mountains, stretching roughly 240 miles from southern Idaho down through Utah. The wall is not vertical. It leans, tilting slightly to the east at depth, diving underground at an angle beneath the Salt Lake Valley. On one side of the wall sits the mountain range, pushed up over millions of years. On the other side sits the valley floor, dropped down as the basin and range extension pulled the crust apart. That wall is the Wasatch Fault, and it has not moved in 1400 years. The Wasatch Fault is what geologists classify as a normal fault, the same type that created every mountain range and valley in the Basin and Range province. The difference between the Wasatch and most other normal faults in the region is scale. The Wasatch is one of the longest and most hazardous normal faults on the continent, with the capacity to produce earthquakes reaching magnitude 7.5 or higher along individual segments. The fault is divided into segments, each capable of rupturing independently or in combination with adjacent segments. The segment sitting directly beneath the Salt Lake City metropolitan area is called the Salt Lake City segment. Geologists have studied it in exceptional detail, digging trenches across the fault surface to expose layers of sediment disturbed by ancient earthquakes, a technique called paleoseismology. What those trenches revealed was a rupture history written in displaced soil and buried boulders. The most recent major earthquake on the Salt Lake City segment left unmistakable evidence in the ground. A surface rupture that dropped one side of the fault several feet relative to the other, folded and fractured soil layers, and left a visible scarp in the landscape. That event occurred approximately 1400 years ago. Since then, silence. No major rupture has disturbed the sediment record on this segment. No surface scarp has formed. The fault has held, locked by friction, absorbing the slow accumulation of tectonic stress year after year, decade after decade, century after century. Geologists calculate the average recurrence interval for major earthquakes on this segment, meaning how often, on average, the fault produces a large rupture. Estimates based on the paleoseismic record suggest recurrences roughly every 1300 to 1500 years. The fault is sitting at the outer edge of that window right now. Not overdue in the way a library book is overdue. Overdue in the way a fault system with known recurrence intervals is approaching or passing its average rupture window, with no release of stored energy in the recorded geologic time since the last event. The underground geometry of the fault amplifies the hazard. Because the fault surface tilts eastward at depth, a rupture on the Salt Lake City segment would not simply shake the valley equally. The footwall, the block of crust on the mountainside, would stay relatively stable. The hanging wall, the block beneath the valley floor, would drop and shake with amplified intensity. The Salt Lake Valley floor is filled with soft sediment, ancient lake deposits left by Lake Bonneville, a massive inland sea that covered much of Utah thousands of years ago. Soft sediment amplifies seismic waves the way a bowl of gelatin amplifies motion compared to a solid table. The same earthquake produces far more violent shaking in soft sediment than in solid bedrock. The city built in that sediment-filled bowl, above that tilted locked fault wall, was growing rapidly and filling its valleys with people and buildings, and the locked wall had just received a stress pulse from 300 miles to the west. In 1847, the first settlers arrived in the Salt Lake Valley and began planning a city. They chose a flat, wide valley with a freshwater source, surrounded by mountains, sheltered from weather. The site was practical and beautiful. What lay beneath the soil was not part of the calculation. They built directly on top of a fault scarp. A fault scarp is a physical ridge or step in the landscape, created when a fault ruptures and one side drops relative to the other. The Wasatch Fault Scarp runs along the base of the mountains on the eastern edge of the Salt Lake Valley, a subtle but measurable rise in the terrain that marks the boundary between the fault's upthrown and downthrown blocks. Early settlers noticed the change in slope, but had no framework to interpret it as a seismic feature. They built their city in the valley below it. Over the following century and a half, Salt Lake City grew into a major metropolitan area. Today, the Salt Lake City metropolitan region holds approximately 2.5 million residents, making it one of the largest urban concentrations in the interior American West. The city has spread outward in every direction, filling the valley floor and climbing into the mountain foothills. Much of that expansion has pushed development directly onto the Wasatch Fault Trace and into the zones of highest shaking hazard. Modern geological mapping has identified the exact location of the fault trace running through the urban area. It passes through residential neighborhoods, beneath commercial districts, under roads and pipelines and critical infrastructure. Some sections of the city that were built decades ago sit directly on the fault zone, meaning the ground beneath them could experience several feet of sudden vertical displacement during a major rupture. Utah has known about the Wasatch fault hazard for decades. The state runs one of the better regional seismic monitoring networks in the American West, maintains an active earthquake preparedness program, and has produced detailed hazard maps identifying the highest risk zones. Building codes in the state require seismic design standards for new construction. The challenge is everything built before those standards existed. Salt Lake City contains thousands of unreinforced masonry buildings, older structures made of brick, without the internal steel reinforcement that allows a building to flex during shaking, rather than collapse. Studies of earthquake risk in the region consistently identify unreinforced masonry as the most dangerous building stock in the city. A major Wasatch Fault earthquake could collapse hundreds of these structures. Infrastructure built across the fault adds another layer of vulnerability. Water mains, gas lines, electrical conduits, and highway overpasses cross the fault trace at multiple points throughout the metropolitan area. Surface rupture along those crossings would sever the lines that keep a modern city functioning. Fires sparked by broken gas lines in a scenario where water mains are also severed created catastrophic secondary damage in historical urban earthquakes. San Francisco in 1906, Kobe in 1995, the fires did as much damage as the shaking. 2.5 million people, a fault beneath their feet, a corridor of traveling stress arriving from the west, and a building inventory that ranges from modern earthquake-resistant construction to century-old brick that has never been tested by a major event. The city exists, the fault exists, the physics connecting the two has been in motion for 14 centuries. The question was never if. The question that scientists debating the 2026 swarm were urgently trying to answer was something much harder. How much closer to that answer had the Nevada sequence just moved the clock? When people hear that the Wasatch Fault has not produced a major earthquake in 1400 years, many take comfort in that number. 1400 years of quiet. 1400 years of no catastrophe. Maybe the fault is less dangerous than scientists say. Maybe the old rupture was the last one. That interpretation has the logic completely backward. Every year of silence on a locked fault is a year of additional stress accumulation, not a year of decreasing danger. The tectonic forces loading the Wasatch Fault have not paused because the fault has not ruptured. The Pacific and North American plates have continued moving past each other at roughly 2 inches per year throughout those 14 centuries. That motion has been feeding stress into the fault system continuously. The fault has stored all of it because it has not slipped to release any of it. Geologists calculate the total slip deficit on the Wasatch Fault, meaning how much the fault surface should have moved by now based on the regional plate motion rate, minus how much it actually has moved. After 1,400 years without a major rupture, the slip deficit on the Salt Lake City segment has grown to somewhere between 10 and 20 feet of stored displacement. 10 to 20 feet. That is the amount of movement the fault is holding back. When the rock finally breaks, some portion of that stored displacement will release in seconds. The ground on one side of the fault will drop relative to the other side by several feet in the span of a rupture that may last 30 to 60 seconds. The shaking that accompanies that movement across a valley filled with soft sediment will be unlike anything recorded in the modern seismic history of the region. The paleoseismic record shows the pattern clearly. Major ruptures on the Salt Lake City segment have occurred multiple times in the geological past, roughly every 1,300 to 1,500 years. The sequence is not random. The fault loads, it breaks, it loads again. The 1,400 years since the last rupture puts the current period at or past the average loading cycle. Scientists examining the paleoseismic trenches dug along the Wasatch Fault trace have documented the physical evidence of past ruptures, tilted sediment layers, buried colluvial wedges of material that fell from the fault scarp, displaced boulders, and soil horizons that jumped suddenly from one side to the other. Each of those features is a record of a moment when the ground dropped suddenly and violently, the same way it will drop when the fault breaks next. The comparison to a compressed spring is overused but accurate for a specific reason. A spring that has been compressed for 14 centuries and is still being compressed by ongoing tectonic forces does not become less dangerous over time. It becomes more dangerous. The energy stored in it grows every year. The compression continues without release. The arrival of the Nevada stress pulse into this system is not by itself certain to trigger the next rupture. The Wasatch Fault may absorb the additional stress and remain locked for additional decades. But the Nevada corridor has added a measurable increment to a system that was already at the outer edge of its historical loading window. A system under extreme stress, at the edge of its historical rupture window, receiving new external loading, is a system that requires serious attention. The 1,400 years of silence are the evidence of how much has accumulated, and the swarm arriving from Nevada is the most recent addition to that total. Tracking an earthquake swarm in real time is not a matter of feeling the shaking and drawing conclusions. It requires a dense network of instruments spread across hundreds of miles of terrain, all feeding data to central monitoring systems simultaneously, 24 hours a day. The Western United States runs one of the most comprehensive seismic monitoring networks on Earth. Hundreds of seismograph stations are buried or anchored at precise locations across Nevada, Utah, and surrounding states. Each station records ground motion continuously, capturing everything from the faintest background tremor to the sharpest main shock arrival. The stations transmit data in near real time, allowing scientists to locate earthquakes within minutes of their occurrence, pinpointing their origin in 3 dimensions: latitude, longitude, and depth. Depth is the dimension most people overlook. 2 earthquakes can share the same surface location but originate at very different depths underground. The depth profile of a migrating swarm tells scientists which part of the fault system is actively slipping and at what level of the crust the stress is traveling. Shallow earthquakes cluster in the brittle upper crust where rock snaps rather than bends. Deeper earthquakes originate where the rock is warmer and more ductile, where aseismic slip is more common and fluid migration more active. The April 2026 swarm produced a depth profile that shifted as the migration advanced. Early earthquakes in the cluster near Fallon were predominantly shallow, consistent with brittle upper crust rupture. As the swarm migrated eastward, some events appeared at greater depths, suggesting the stress was traveling at multiple levels of the crust simultaneously. through different physical mechanisms operating at different depth zones. Scientists used this combined spatial and depth data to construct a three-dimensional picture of the migrating stress front. The picture showed a complex, multi-layered advance, shallow fluid-driven events at one level, deeper aseismic-driven events at another, both moving east along the corridor at rates that, while slightly different, pointed toward the same general destination. Strain meters added another dimension to the picture. These instruments measure the extremely slow, continuous deformation of the ground surface as stress builds or releases in the crust below. During the swarm, strain meter readings across the Walker Lane region showed patterns consistent with broad crustal deformation, extending well beyond the visible earthquake cluster. The footprint of the event, measured in ground deformation, was larger than the cluster of seismic dots on the migration map suggested. GPS stations contributed the longest range view. By comparing precise GPS measurements before and during the swarm, scientists detected subtle ground movements across the entire region, millimeter-scale shifts in the relative positions of monitoring stations that reflected the cumulative effect of all the seismic and aseismic activity across the corridor. The picture assembled from all of these instruments was detailed, three-dimensional, and alarming. A stress front advancing eastward through multiple levels of the crust, leaving signatures in seismograph records, strain meters, and GPS data simultaneously. Arriving at the base of the Wasatch Mountains with enough residual energy to register on instruments calibrated to detect the faintest ground signals, and on the other side of those mountains, in the valley that 2.5 million people called home, the monitoring stations were recording something they had not recorded before in the modern era: a sustained background increase in microseismic activity along the Wasatch Front itself, small, barely above noise level, but present, and trending in one direction. The state of Nevada is leaving North America, slowly, imperceptibly, over geological timescales that dwarf human civilization, but measurably, continuously, and confirmed by GPS satellites tracking the motion of the ground beneath your feet. The Walker Lane is the mechanism of that departure, a zone of shearing, rotating, and extending crust that is gradually redefining the western boundary of the continent. The process is called tectonic escape. As the Pacific Plate grinds northwestward past the North American Plate, the region of crust caught between them does not simply stay still and absorb the collision. Parts of it begin to move with the escaping flow, rotating, translating, shearing sideways. The Walker Lane captures that motion and distributes it across hundreds of miles of fractured, mobile crust. GPS measurements taken over several decades show that blocks of crust within the Walker Lane are moving at measurable rates relative to the stable interior of North America. The motion is not uniform. Different blocks move at different speeds and in slightly different directions, producing the complex shearing and rotating pattern that defines the zone. But the net effect, summed across the entire system, is a steady transfer of crustal material from the interior of Nevada toward the northwest, following the pull of the Pacific Plate. The rate has been increasing. Early GPS campaigns in the 1990s measured the motion. Later campaigns, with higher precision instruments and longer baselines of data, showed the rate of Walker Lane movement has accelerated compared to earlier estimates. The zone is capturing a larger fraction of the plate boundary motion over time, progressively taking load from the San Andreas system to the west. For earthquake hazard, this acceleration has direct consequences. A fault system moving faster accumulates stress faster. More stress per year means shorter occurrence intervals for major earthquakes. A fault that historically broke every 500 years might break every 400 years if the loading rate increases by 20%. The math is simple, the implications are not. The eastern boundary of the Walker Lane is where this shearing motion runs out of room. The Colorado Plateau and the stable craton of the North American interior resist the motion. The crust cannot escape eastward because the stable plate blocks the way, so the stress concentrates at the boundary, loading the faults that line the transition zone between moving and stable crust. The Wasatch Front is that boundary. All the shearing, rotating, translating motion of the Walker Lane ultimately pushes against the Wasatch Front. The fault system there is the dam holding back the accumulated motion of the entire zone. Every year the Walker Lane speeds up, more stress arrives at that dam. Every year the dam holds without breaking. More energy stores behind it. The 2026 swarm was a visible symptom of this larger, slower process. A seismic announcement that the system was active, loaded, and transferring energy eastward at an elevated rate. Not an isolated event, but a momentary peak in a process that has been building for millions of years and is currently in an active phase. The Walker Lane is not going to stop moving. Nevada is not going to stop departing. The boundary fault at the eastern edge of that departure is not going to stop accumulating stress. The only variable is when the accumulated stress reaches the threshold that the rock can no longer hold. That threshold, and how close the Wasatch Fault is to it right now, is the question that no current instrument can definitively answer. But what scientists have been quietly modeling is a scenario that, if it occurs, would rank among the most destructive natural disasters in American history. Regional cascade ruptures are the events seismologists discuss carefully in measured language, because the scenarios they describe are extreme enough to sound like exaggeration. They are not exaggeration, they are physics. A cascade rupture occurs when one earthquake loads adjacent faults past their breaking points, triggering ruptures that in turn load the next faults in the chain, producing a sequence of major earthquakes across a wide region in a compressed time frame, hours, days, or weeks rather than the centuries of normal geological accumulation. The energy does not all release at once in a single superquake. It releases in a rapid succession of major events, each one generating its own damage before the region has recovered from the previous hit. The 1954 Nevada sequence, covered earlier, was a small-scale demonstration of the mechanism. 3 major earthquakes inside 4 minutes along connected basin and range faults. That sequence stayed within Nevada and affected a sparsely populated region. The structural principle was the same as a larger cascade. The consequences were limited by geography and population density. The American West came closest to a regional cascade in 1992, in California. The magnitude 7.3 Landers earthquake ruptured 4 separate fault segments in the Mojave Desert in a single event, the longest fault rupture in California in the 20th century. Within hours, a magnitude 6.5 struck near Big Bear, triggered by the stress change from Landers. Within days, volcanic tremor increased at Mammoth Lakes, hundreds of miles to the north. As the seismic waves disturbed hydrothermal systems, earthquake rates rose across the entire western United States for weeks. Scientists studying Landers concluded it had come close to triggering larger events on the San Andreas Fault. The stress increase on certain San Andreas segments was measurable and significant. The San Andreas held. But the analysis showed how close a well-timed stress pulse on a critically loaded fault can push a regional system toward a cascade. The basin and range is structurally more vulnerable to cascading than California's fault systems in certain respects. The network of parallel faults, all under continuous extension, means stress transferred from one fault reaches many others simultaneously, rather than traveling along a single corridor. A major rupture in a loaded region of the basin and range fans its stress outward across a wide web of faults, each of which might be within reach of its own failure threshold. A cascade beginning with a Wasatch Fault rupture of magnitude 7 or higher would load faults throughout the Salt Lake Valley and beyond. The specific geometry of the Wasatch Front fault system means that rupture on one segment transfers stress to adjacent segments, above and below it. Historical paleoseismic records show evidence of multiple segment ruptures occurring close together in geological time along the Wasatch system, suggesting the precedent for cascade-style sequential rupturing already exists in the fault zone history. The The 2026 Nevada swarm did not trigger a Wasatch cascade, but it demonstrated the connectivity of the system and the active state of the stress field driving it. It revealed the plumbing, and it confirmed that the plumbing runs directly from an active seismic source in Nevada to the most dangerous locked fault in the interior American West. Whether the Nevada swarm was the first tremor in a longer sequence, or an isolated elevated event that will fade without consequence, is the question that every seismologist watching this region was trying to answer. And the honest answer, as of the end of the observation window, was that they could not be certain. The most uncomfortable truth in earthquake science is this: the tools available to monitor earthquakes are sophisticated enough to see everything that is happening, but not yet precise enough to predict what happens next. Scientists watching the April 2026 Nevada swarm had access to data that researchers 50 years ago could not have dreamed of. Real-time seismograph networks, GPS deformation measurements updating hourly, strain meters buried at strategic points across the corridor, satellite-based radar measuring millimeter-scale ground surface changes across entire states, borehole sensors recording fluid pressure at depth. The monitoring infrastructure was dense, modern, and operating continuously. All of that data told researchers exactly what the swarm was doing. It could not tell them what the swarm was going to do. The fundamental limitation is that earthquake prediction requires knowing the precise stress state of a fault at every point along its surface, down to the level of individual rock contacts and fluid pressures in microfractures. The scale of detail required is far smaller than any instrument can resolve from the surface or from sparse borehole measurements. The interior of the crust is effectively invisible at the resolution needed to make confident rupture forecasts. What scientists can do is calculate probabilities. They can take everything known about the fault geometry, the loading history, the current stress state estimated from models, the migration behavior of the swarm, and produce a range of possible outcomes with associated likelihoods. During the 2026 sequence, multiple research groups ran these calculations and published their preliminary findings. The range of outcomes those calculations produced was wide. On one end, the swarm was a self-limiting fluid-driven event that would decay naturally within 90 days, dissipating its stress into background noise without triggering major rupture on any additional fault. On the other end, the swarm was the beginning of a foreshock sequence that would culminate in a major rupture on the Wasatch Fault, or along the corridor, similar to how the small events preceding the 1994 Northridge earthquake in California looked unremarkable until the large event that followed them. Distinguishing between these outcomes in real time is nearly impossible with current technology. A foreshock sequence and a decaying swarm can look identical in their first weeks. The only reliable distinction is retrospective. If a large earthquake follows, the earlier events were foreshocks. If the sequence decays quietly, they were a swarm. The label gets applied after the fact. Emergency management decisions, however, cannot wait for retrospective classification. Decisions about whether to issue public advisories, pre-position emergency resources, conduct building inspections, or upgrade response posture must be made in real time on the basis of incomplete information, with consequences either way. Issuing a warning that turns out to be unnecessary erodes public trust in the science and makes future warnings less effective. Failing to communicate elevated risk when a sequence later produces a major event generates a different kind of institutional failure. Scientists and emergency managers navigating this tension were doing exactly that during the spring of 2026. The probability estimates were elevated above background levels. That much was clear and agreed upon. How elevated and for how long the elevation would persist remained genuinely uncertain. The swarm had already violated standard decay models once. There was no guarantee it would not do so again. What happened inside that 90-day window, and what the instruments recorded as the weeks passed, would determine which end of that probability range this sequence belonged to. Nevada generates more geothermal electricity than any other state in the continental United States. That is not a coincidence. It reflects the geology directly beneath the surface, a region where the Earth's internal heat sits closer to the surface than almost anywhere else on the continent. The Basin and Range province has thin crust. All that stretching and thinning over millions of years has pulled the crust down to a fraction of its original thickness in places. Where the crust is thin, heat from the Earth's interior conducts upward more efficiently. The boundary between the cooler crust and the hot mantle beneath it sits relatively close to the surface, and the heat flowing upward through that thinned crust is intense enough in many locations to boil water at moderate depths. Boiling water at depth under pressure does not stay liquid. It becomes high-pressure geothermal fluid, a mixture of superheated water, steam, and dissolved minerals that rises through whatever pathways it can find. The fractured crust of the Walker Lane provides abundant pathways. Faults and fractures that in a cold, dry environment would be sealed by mineral deposits instead become plumbing, channeling fluid upward and laterally through the rock. This thermal system is not static. Geothermal fluid circulation in the Walker Lane changes dynamically in response to tectonic stress. When faults slip, new fractures open. Fresh pathways let fluid move into areas previously sealed. Pressure gradients shift. Fluid that had been pooling in one location finds a new route and begins migrating. The April 2026 swarm opened new fractures across the Walker Lane corridor. Each earthquake ruptured additional pathways through the rock. Those new pathways gave the pressurized geothermal fluid fresh routes to travel. Scientists, studying the swarm's behavior, noted that the migration rate fluctuated in ways consistent with episodic fluid breakthrough events. Moments when the fluid front penetrated a new section of the fracture network and suddenly advanced farther and faster than the average rate suggested. Each breakthrough lubricated a new section of fault, lowered the friction there, and set up the next earthquake in the chain. The geothermal system is also self-reinforcing in a specific way. As fluid migrates and faults slip, the heat flow from the mantle into the fractured zone increases slightly because broken rock conducts heat differently than intact rock. More heat means more fluid circulation. More fluid means more lubrication. More lubrication means more slip. The system feeds itself, which is part of why fluid-driven swarms in geothermally active regions tend to last longer than purely mechanical aftershock sequences. Understanding the thermal system beneath the Walker Lane corridor is critical for predicting how long the swarm's fluid-driven component will remain active. Fluid-driven seismicity in well-mapped geothermal systems has lasted from weeks to years depending on the volume of fluid involved and the permeability of the fracture network. For the 2026 sequence, scientists lacked the subsurface fluid volume data needed to confidently bound the duration. The heat driving the fluid has been present in this region for millions of years. It will continue regardless of what the swarm does. The fractures opened by the swarm will remain, at least partially, as new pathways for future fluid migration. The plumbing that drove this swarm is permanent, and it connects, underground, to the fault corridor that was still carrying stress eastward toward Utah. Every model scientists built of the 2026 Nevada swarm rested on assumptions. Assumptions about fault geometry at depth, assumptions about fluid pressure distribution underground, assumptions about the exact mechanical properties of the rock along the corridor, assumptions about where the fault surfaces were most locked and where they might be partially creeping. Those assumptions existed because the data required to replace them with measurements does not yet exist. Mapping the subsurface of the crust in 3 dimensions at the resolution needed for accurate earthquake prediction requires direct access to the rock at depth. Boreholes, the cylindrical holes drilled deep into the earth to collect rock samples and insert sensors, provide the only direct measurements of deep crustal properties. But drilling deep enough to characterize a fault system at seismogenic depths, the depths where earthquakes actually occur, costs tens of millions of dollars per hole and produces a single data point in a fault system stretching hundreds of miles. The Walker Lane corridor has a sparse borehole network. the sections of the fault system most critical to understanding the 2026 migration, the deep connections between individual fault segments, and the exact geometry of the fault surface beneath the corridor, have almost no direct sampling. What scientists knew about those sections came from surface geology, seismic reflection surveys, and earthquake location data, all of which provide indirect evidence about the subsurface rather than direct measurement. Seismic reflection surveys, the most powerful remote sensing tool available for subsurface mapping, work by sending controlled sound waves into the ground and recording the echoes as they bounce off different rock layers. The echoes reveal the geometry of structures underground, including fault surfaces, but resolution decreases with depth, and the fracture network of the Walker Lane is complex enough at depth that reflection surveys produce ambiguous images in critical zones. The result is that the three-dimensional picture scientists used to model the swarm had sharp detail near the surface and increasingly blurry detail at depth. The deeper the fault features involved in the migration, the less certain the geometry and the less certain the prediction of how stress was distributing across the corridor. For the Wasatch Fault specifically, paleoseismic trenching had produced excellent documentation of past surface ruptures, but the behavior of the fault at depth, where the slip initiated and how the rupture would propagate across multiple segments, remained incompletely characterized. A fault that initiates its rupture on one segment might propagate to an adjacent segment under certain geometric conditions and stop at the segment boundary under other conditions. Which scenario would apply to the Wasatch depended on subsurface geometry that the available data could not resolve. This is the honest state of the science, powerful, sophisticated, and genuinely useful at the level of regional hazard assessment, but operating with fundamental gaps in subsurface knowledge that prevent the precise, location-specific, timing-specific predictions that emergency management would need to act with confidence. Scientists are not withholding a secret precise forecast. The precise forecast does not exist yet. The instruments and drilling programs that would generate the needed data are future technology and future investment. For the 2026 swarm, decisions were made on the best available incomplete picture. That picture was alarming enough on its own. Drive east from Fallon, on Highway 50, and eventually the road crosses the Dixie Valley. The valley is wide and flat, the kind of place where the sky feels enormous and the silence feels physical. There is almost no development, almost no traffic, just desert, mountain edges, and the flat, ancient lakebed floor stretching toward the horizon. And then you see it. A line in the landscape, a step in the terrain running roughly parallel to the mountain range, visible from a distance, growing more dramatic as you approach. On one side of the line, the ground sits several feet higher than on the other side. The transition is not gradual, it is abrupt. A clear physical boundary where the earth dropped on one side and stayed up on the other. This is the Dixie Valley Fault Scarp from the December 1954 rupture. 70 years later, it is still there, unchanged, carved into the desert floor as clearly as the day it formed during those 4 minutes when 3 major earthquakes tore through central Nevada in rapid succession. Fault scarps form in seconds during earthquake rupture. One side of the fault drops relative to the other. The ground surface on the downthrown side falls away, creating a step, a cliff, a long linear ridge, visible from miles away. In a humid climate, erosion quickly softens these features. Vegetation grows over them, rain rounds the edges. Within centuries, they can become nearly invisible in the landscape. In the Nevada desert, erosion is minimal, rain is rare, vegetation is sparse. The scarps from 1954 are as sharp and fresh-looking today as they were when they formed. Scientists studying fault scarp morphology use the Dixie Valley Scarp as a calibration reference precisely because its age is known and its original geometry is so well preserved. The scarp is not just a geological curiosity, it is a measurement. The amount of vertical displacement across the scarp, several feet along most of its length, represents the amount of slip that occurred on the Dixie Valley Fault during the December rupture. That displacement, mapped in detail along the length of the scarp, tells scientists the exact geometry of the 1954 rupture and how stress distributed across the fault surface during the event. Data from the Dixie Valley Scarp contributed directly to models of how the Walker Lane fault system behaves during major cascading sequences. The 1954 ruptures demonstrated that faults in this region can transfer enough stress to trigger adjacent major ruptures within minutes. The geometry of those transfers, documented in the Scarp record, informed the calculations scientists ran during the 2026 swarm about how stress was moving through the corridor. The Scarp also offers a ground-level demonstration of scale that numbers alone cannot provide. Standing at the base of the Dixie Valley Fault Scarp and looking up at a wall of displaced earth several feet high, stretching as far as you can see in both directions, produced by 30 seconds of shaking on a quiet December night in 1954, with almost no one nearby to experience it, gives physical form to what the same energy would mean beneath a city of 2.5 million people. The desert absorbed it. The record it left is the warning. Seismologists and engineers have modeled a major Wasatch Fault earthquake in exhaustive detail. The scenario has a formal name inside Utah emergency management circles. The models are specific, grounded in physics, and the results are severe. A magnitude 7 rupture on the Salt Lake City segment of the Wasatch Fault, initiating on the segment beneath the urban core and propagating north and south along the fault trace, would generate peak ground accelerations across the Salt Lake Valley, reaching levels that exceed the design threshold for most pre-1990s construction in the region. What that means in plain language, the shaking would be strong enough to damage or collapse a large fraction of older buildings in the city. The soft sediment beneath the Salt Lake Valley amplifies ground motion significantly compared to bedrock sites. Engineers call this site amplification. The ancient lake sediments left by Lake Bonneville, which once covered much of Utah to a depth of over 1,000 feet, before draining roughly 14,000 years ago, are hundreds of feet thick in parts of the valley. Seismic waves traveling through that thick, water-saturated sediment slow down and grow in amplitude, the same way a wave grows taller as it enters shallow water near a beach. Studies of site amplification in the Salt Lake Valley suggest that shaking at some sediment-covered locations could be 2 to 4 times more intense than at nearby bedrock sites during a major Wasatch event. The neighborhoods with the deepest, softest sediment would experience the most violent shaking. Much of the urban core sits on exactly that kind of ground. Unreinforced masonry buildings, brick structures without internal steel reinforcement, make up a significant portion of older residential and commercial stock in Salt Lake City. Engineering studies of these buildings consistently reach the same conclusion. They perform poorly in moderate shaking and catastrophically in severe shaking. Walls lose lateral support and collapse inward. Roofs fall. The buildings do not simply crack, they come down. After the shaking stops, secondary hazards activate. Gas lines severed by ground rupture or strong shaking leak into structures and the soil. If an ignition source is present, fires start. In a scenario where water mains are simultaneously broken by fault rupture crossing pipeline infrastructure, fire suppression becomes severely limited. The 1906 San Francisco earthquake killed more people through fire than through the initial collapse, and that occurred before the city had its current density and fuel load. Transportation disruption would isolate parts of the city within hours. Highway overpasses crossing the fault trace could fail, cutting the primary access routes between the eastern and western parts of the metropolitan area. Emergency responders from outside the region would face severely degraded road networks trying to reach the affected zone. The models project thousands of casualties in a worst-case segment rupture scenario, with tens of thousands of people displaced from damaged or destroyed housing. The economic cost projections reach into the hundreds of billions of dollars when direct damage, infrastructure replacement, and economic disruption are combined. These models existed before the 2026 swarm. They were built over decades of careful engineering and seismic hazard analysis. The swarm did not create the risk. It reminded the region, in real time, that the risk was not theoretical. In earthquake science, 90 days is a benchmark, an informal but widely referenced threshold that separates the acute phase of a seismic sequence from its chronic phase. Most earthquake sequences follow a recognizable arc: main shock, rapid aftershock decay, gradual taper, quiet. The entire sequence from main shock to background levels typically plays out within 30 to 90 days for events of the magnitude range seen in the Nevada swarm. By the 90-day mark, a sequence that is going to decay on its own has usually shown clear signs of doing so: declining event frequency, shrinking magnitude range, stable spatial footprint. A sequence that reaches the 90-day mark without meeting those criteria falls outside the standard model. Seismologists then begin evaluating the sequence under a different framework, one that treats the continued activity as potentially driven by a sustained mechanism rather than simple post-rupture relaxation. For the April 2026 Nevada swarm, the 90-day clock started on April 5th and ran to approximately July 5th. Scientists monitoring the sequence tracked daily event counts, magnitude distributions, and spatial footprint throughout that window, comparing the observed behavior to decay models calibrated from historical sequences in the Basin and Range province. The May 1st magnitude 5.2 was itself a violation of standard 90-day expectations. A second major event, 26 days into a sequence that should have been tapering, was a data point that pushed the probability distribution toward longer duration mechanisms. If the swarm reached the 90-day mark, still producing elevated activity, still migrating, still generating events above magnitude 4, the implication would be significant. A sustained mechanism, whether long-duration fluid migration or a deeper aseismic slip episode, would still be actively driving the stress transfer. The corridor would still be pumping energy eastward. The Wasatch fault would still be receiving an active stress input rather than absorbing a fading pulse. The practical difference matters enormously for hazard assessment. A fading stress pulse loads the Wasatch fault by a fixed amount and then stops. The fault absorbs the increment and remains locked. A sustained mechanism continues adding stress incrementally over months, potentially pushing the fault past its threshold at some point during or after the active loading period, rather than immediately. Sustained loading scenarios give emergency managers a longer decision window in one sense. The event does not need to happen within days of the Nevada swarm, but they create a more complex risk landscape because the threat remains elevated over a longer period, making it harder to communicate to the public without either creating alarm fatigue or under-communicating a genuine elevated risk. Scientists watching the July 5th mark approach had their instruments calibrated and their models updated. The data from that period would not definitively answer the foreshock versus swarm question, but it would significantly narrow the probability range and inform the next stage of hazard assessment for the Wasatch Front. What the instruments showed as the calendar moved through those 90 days would determine how the conversations in geology offices, emergency management centers, and eventually public briefings would shift in the months that followed. Seismologists studying the 2026 Nevada swarm were not unified on its driving mechanism. Two leading explanations competed for the data, each supported by different subsets of the evidence, each carrying its own alarming implications for what might happen next. The first theory is pressurized fluid migration. Deep geothermal fluids, superheated by the intense heat flow beneath the thinned basin and range crust, enter the fractured fault network and migrate along the connected pathway toward the east. As they travel, they reduce friction on fault surfaces and trigger the earthquakes observed along the corridor. The migration rate of 1 to 2 miles per day is consistent with fluid-driven sequences documented in other geothermally active regions around the world. The episodic bursts of accelerated migration match the behavior of fluid breaking through newly opened fracture networks. The deep tremor signals, across the corridor reflect the acoustic signature of fluid movement through rock. Under the fluid theory, the swarm has a natural endpoint. Fluids carry finite energy and finite pressure. As they travel and spread through the fracture network, the pressure equalizes. Friction returns. Fault surfaces relock. The earthquakes stop. The timeline for this equalization depends on the volume and pressure of the original fluid source, quantities that scientists could not precisely measure in the 2026 sequence. The process could end in weeks or continue for over a year. The terrifying aspect of the fluid theory is the uncertainty in that timeline. Fluid-driven sequences in volcanically and geothermally active regions have lasted for years in some documented cases. A multi-year sustained stress transfer toward the Wasatch Fault, even at low incremental rates, produces a cumulative loading effect that is difficult to dismiss. The second theory is aseismic slip. Deep in the crust, below the brittle zone where standard earthquakes occur, the rock deforms slowly and silently. A large aseismic slip event is essentially a very slow earthquake, releasing stress over weeks or months instead of seconds. The slow slip transfers its load onto the brittle faults above and ahead of it, triggering the visible earthquakes that mark its passage. Aseismic slip events in subduction zones have been extensively documented, but their occurrence in the basin and range extensional environment is less well characterized. Under the aseismic slip theory, the swarm is a surface expression of a much larger, deeper and slower event happening beneath it. The visible earthquakes are symptoms, not the main event. If a large aseismic slip episode is moving through the crust beneath the Walker Lane corridor, it carries far more energy than the visible seismicity suggests, and delivers that energy to the Wasatch Fault with greater efficiency than fluid migration alone. The terrifying aspect of the aseismic slip theory is precisely its silence. Fluid migration leaves acoustic signatures. Aseismic slip, by definition, does not. Scientists inferring its presence from strain meter anomalies and GPS data are working with indirect evidence that cannot precisely locate the slip or measure its total magnitude. A large aseismic slip event could deliver a substantial stress increment to the Wasatch Fault and leave no clear seismic announcement that it had done so. Both theories predict stress reaching the Wasatch Fault. Both predict that stress is a meaningful increment above background levels. The debate between them is about mechanism and magnitude, details that determine the risk level but do not change the fundamental direction of the story. Either way, the fault beneath Salt Lake City was receiving more stress in the spring of 2026 than it had in any comparable period in the modern monitoring era. The Wasatch earthquake scenario has sat in Utah emergency management files for decades. The risk has been formally assessed, modeled, and incorporated into planning documents that most residents never read, and most news cycles never cover. The 2026 Nevada swarm did not introduce the hazard to emergency planners. It elevated the urgency of preparations that were already underway. Utah's Division of Emergency Management and the Salt Lake City Office of Emergency Management coordinate with federal agencies, academic researchers, and regional partners on Wasatch Fault preparedness continuously. The planning work is technical, detailed, and largely invisible to the general public, which is partly by design and partly a reflection of the difficulty of communicating long-range seismic risk without generating unproductive alarm. Building vulnerability assessments are one active component. Engineers contracted by the city and state have been systematically evaluating older unreinforced masonry structures throughout the urban core, identifying the highest risk buildings, and developing retrofit priority lists. Retrofitting a masonry building to modern seismic standards requires adding steel reinforcement to walls and connections, a process that costs tens to hundreds of thousands of dollars per structure and requires temporary displacement of occupants. The scale of the inventory requiring attention exceeds the current pace of retrofit funding. Critical infrastructure mapping is another ongoing effort. Water system operators have identified the segments of the Salt Lake City water distribution network most vulnerable to fault rupture. Emergency bypass routes and alternative supply connections have been engineered into the system in some zones, allowing operators to reroute flow around broken segments after a major earthquake. The goal is to maintain fire suppression capacity in the hours immediately following an event, when the risk of secondary fire is highest. Hospital preparedness received attention in the planning cycles leading up to and following the 2026 swarm. A major Wasatch rupture would generate mass casualty numbers that would overwhelm local medical capacity almost immediately. Regional mutual aid agreements identify which hospitals outside the immediate damage zone would receive patient transfers and which facilities would serve as field treatment sites. The planning assumes that some fraction of Salt Lake City's hospital infrastructure would itself sustain damage, removing capacity at exactly the moment demand peaks. Communication infrastructure vulnerability is a planning gap that emergency managers acknowledge openly. Cellular networks rely on towers that themselves could sustain damage, and the traffic spike immediately following a major earthquake typically overwhelms remaining capacity. Backup communication plans rely on radio networks and pre-positioned satellite terminals, but coverage is not complete across the entire metropolitan area. Schools have received seismic evaluation, and many older school buildings have been retrofitted or replaced with new construction, meeting current seismic codes. The retrofit program for school facilities has moved faster than for commercial or residential stock, reflecting the political priority placed on child safety. All of this preparation existed before April 2026. The Nevada swarm accelerated conversations about timeline and resource allocation. Emergency planners who had been working on multi-year improvement schedules began revisiting whether certain priority actions needed to move faster. The public, by and large, continued with ordinary life. 2.5 million people buying groceries, driving to work, sleeping in buildings that had never been tested by a major earthquake, the preparations happening quietly around them, were real and meaningful. They were also incomplete, and the fault beneath the valley floor was not on a schedule that emergency planners could control. Every seismologist tracking the April 2026 Nevada sequence carried some version of the same question through the spring and into summer. Is this ending? Or is this the beginning? The data available did not resolve it. It could not. Earthquake sequences reveal their nature retrospectively, and the 2026 swarm was still in progress. Scientists built probability ranges, not certainties. They updated those ranges as new data arrived. They communicated their uncertainty with precision and watched the public struggle to interpret probability language in a way that would drive appropriate action. Probability is a difficult concept to act on. A 10% chance of a catastrophic event is genuinely small. It is also genuinely 10 times more likely than a 1% chance of the same event. For a population of 2.5 million people, a 10% chance of a major fault rupture in a given year is a hazard that demands serious attention, even if 90% of the probability weight says nothing happens. The swarm, as of the end of the documented observation period, had produced over 400 earthquakes across 18 days, followed by a second significant main shock 26 days after the first, followed by sustained migration activity pointing toward the Wasatch Front. The sequence had violated standard decay models. It had activated faults along a 310-mile corridor. It had generated detectable stress changes at the eastern end of that corridor, and it had occurred at a time when the Wasatch Fault was already sitting at the outer edge of its historical loading window. Each of those facts, individually, would be worth monitoring. Together they described a seismic situation without a clear modern precedent in the Basin and Range region. The two possible futures remained open. In one future, the swarm decays quietly over the following months. The fluid pressure equalizes. The aseismic slip slows. The visible earthquake activity tapers toward background levels. The stress increment delivered to the Wasatch Fault is real but insufficient on its own to trigger rupture, absorbed into the fault's total stored energy as one more increment among 14 centuries of accumulation. The Nevada swarm becomes a significant scientific case study, a data set for refining migration models and improving subsurface mapping. Life in Salt Lake City continues. The Wasatch Fault remains locked, waiting for its own time. In the other future, the swarm does not decay quietly. The sustained mechanism, whether fluid or a seismic slip, continues driving stress eastward through the summer. The stress increment arriving at the Wasatch Fault crosses a threshold. A rupture initiates on the Salt Lake City segment, propagates along the fault, drops the hanging wall of the valley several feet in 30 seconds of violent shaking, and sends millions of people into a disaster scenario that planners had modeled but never experienced. Both futures were physically possible. The physics did not rule either one out. What science could offer with confidence was this. The April 2026 Nevada earthquake swarm revealed active, connected, migrating seismic energy traveling through 310 miles of mechanically continuous fault structure toward one of the most hazardous and most populated sections of the American West. The monitoring infrastructure saw it, the models tracked it, the history of the region provided context for how badly such transfers of stress can end. The Wasatch Fault has broken before. The scarred sediment layers in the paleoseismic trenches are the proof. It will break again. The question the 2026 swarm could not answer, and that no instrument built today can answer, is whether the calendar for that next break just moved closer. The ground beneath Salt Lake City is still. The fault beneath that ground is loaded, and somewhere deep in the fractured crust of the Nevada desert, the Earth is still deciding what it does next.